Hello, we are help each other. Our team consists of leader Na Yun-ho and members Kang Dong-ho, Ryu Tae-hwan, Chang Min-seok, and Choi Jae-hoon. Today we will present our exploratory study of the optimal electrical characteristic of IGZO TFT. Let's begin the presentation. As you can see in this page, we will announce it in this order. First, background. Have you ever heard of TFT? TFT means thin film transistor, and you can find in various display devices such as TVs, computers, and smartphones. These transistors combust in the form of thin films. TFT consists of two main types according to how it acts. One is drive TFTs, which boost the electrical signal, and the other one is switch TFTs, which act like on-off switches. The material used in TFTs can be grouped into three categories: amorphous silicon, LTPS, and oxide. Traditional TFTs often use amorphous silicon and LTPS for active layer. Amorphous silicon is cheap and easy to make, but is not suitable for high-quality displays because it doesn't let electricity flow well. On the other hand, LTPS has better electrical flow, but is expensive to make and has poor uniformity, so it has limits for large display. To overcome this limitation, researchers have been focused into oxide TFTs. These TFTs have high electron mobility in amorphous form, also high uniformity, low threshold voltage, and low cost. These characteristics make oxide TFTs are suitable for high quality and large area displays.
Next is our experiment objectives. First of all, taking advantage of previous characteristics, our plan is to make IGZO TFT suitable for large displays. We will deposit IGZO active layer on the silicon wafer, and then deposit TI moly electrode using a shadow metal mask. Secondly, we are going to adjusting the fabrication parameters. For example, power, pressure, and gas partial pressure. Thirdly, measure the electrical characteristics and analyze the data. Through the third step, we can compare the electrical characteristics based on the adjusted variable and proceed with the feedback process on the experiment. Lastly, optimize devices through fabrication parameters, control and post-processing. Detailed explanation for each step will be provided later. Now let's talk about IGZO TFT. First of all, IGZO TFT is a transparent oxide semiconductor with an oxide active layer. IGZO have a 3.2 electron volt band gap energy, allowing it to transmit light in the visible spectrum. In IGZO, each atom has a role. Indium creating a high electron mobility through the orbital overlap, and then gallium reducing oxygen vacancies and suppressing excessive carrier production to reduce off current. Next is zinc. Zinc stabilizes the structure and contribute to carrier generation via interstitial zinc. And finally, oxygen contribute to generating oxygen vacancies.
Next is our experiment process. Let me introduce our electrode deposition materials. Typically, metals are deposited as electrodes onto IGZO layer with two contact methods based on the metal's work function compared to semiconductor. Two contact is ohmic contact and Schottky contact, where we choose ohmic contact to reduce the potential barrier between the electrode and IGZO. So we can get increasing drive currents and decreasing power consumption. But weakness is potentially increasing leakage current. Next, we deposited molybdenum over the titanium to enhance conductivity. Typically, electrode deposition needs through etching process, but we use shadow metal mask for deposition. This decision aims to avoid surface defects and improve efficiency compared to etching process. Using shadow metal mask reduces the cost and defects. And this is our shadow metal mask. This page, we show our TFT's operation diagram easily. First, injected the gate voltage. Then polarization occurs inside the silicon oxide and channel is formed in the IGZO. Next, we injected drain voltage. Now, electrons can move from source electrode to drain electrode because of potential difference.
The picture on the left is the IGZO TFT we fabricated. Looking at the table on the right, variables written in black were fixed based on the values listed in the table, while variables written in red were adjusted to proceed with the process. Next is our measurement process. We will measure the electrical characteristics of IGZO TFT through two methods displayed on the screen. Firstly, we will measure the on-off ratio, threshold voltage, and the sub-threshold swing through the transfer curve, and compare and analyze the measurement values before and after post-processing step. Secondly, we will measure the electron mobility and charge carrier concentration through hole measurement, and compare and analyze the measurement values before and after post-processing step. We measured the electrical characteristic of IGZO TFTs fabricated by adjusting the oxygen partial pressure ratio among the process variables. We obtained graph on the screen after measurement. Through this graph, we could determine the electrical characteristic values. Among them, we will proceed experiment by adjusting the process variables to obtain better characteristic values for sub-threshold swing and on-off ratio.
I will explain the future plan. The furnace usage plan is as follows. The summer running temperature is set to 200 Celsius and 300 Celsius. The summer running time is fixed to 2 hours. Atmospheric conditions will be created in an O2 atmosphere. The expected post-processing effect is: first, reduce off current; second, reduce back channel effect; third, improve crystallinity; fourth, improve sub-threshold voltage swing characteristic. We are going to adjust the variable after measuring the transfer curve. Also, we are going to measure through hole measurement after optimization. And as we said before, we are going to proceed with post-processing through furnace. Thank you for listening to our presentation so far.